Hey everyone, ready for some mind-blowing physics?
Always up for a cosmic adventure.
Awesome. Today we're diving deep into the biggest physics discoveries of 2024.
That's right, and our guide for this journey.
This fantastic article from Quanta Magazine, of course.
Get ready to impress your friends with some serious science trivia.
You'll be the life of the party. So let's jump right in with something that always throws me for a loop. Dark energy.
Dark energy.
The universe is not just expanding, but accelerating. It's like some invisible force is pushing everything apart.
Exactly, and that invisible force is what we call dark energy. It's one of the biggest mysteries in cosmology.
Back in 1998, when scientists discovered this accelerating expansion, it totally revolutionized our understanding of the universe.
It really did. And now there's a hint that dark energy itself might be changing.
Oh, wow, really? Tell me more.
Well, there's this incredible project called the Dark Energy Spectroscopic Instrument, or DII for short.
DSI, I've heard of that.
It's creating a massive 3D map of galaxies, tracking how the universe has expanded over billions of years.
That's amazing, like a cosmic time machine.
Exactly. And the latest data from DSI suggests that the rate of acceleration might be decreasing.
Hold on, decreasing. So dark energy might be weakening.
That's the tantalizing hint. It's like finding out that gravity isn't constant after all.
Whoa! If that's true, it throws a wrench into everything we thought we knew.
It would completely change our understanding of cosmology. We've always assumed dark energy is constant.
If it can weaken, what does that mean for the future of the universe?
That's the big question, isn't it? Will the universe keep expanding, or could it start contracting?
A big crunch. Everything collapsing back in on itself. Mind officially blown.
It's one possibility, but we need more data to confirm these findings.
Speaking of mind-blowing, let's move on to another cosmic puzzle, dark matter. We can see its gravitational effects, but we still can't directly detect it.
Yes, dark matter, the invisible stuff that makes up most of the universe's mass.
And for decades, scientists have been searching for these elusive particles called WIMPs.
Right, but there's a snag in the WIMP hunt.
What's that?
Well, our detectors are becoming so sensitive that they're getting swamped by solar neutrinos.
Solar neutrinos, those tiny particles from the sun.
Exactly. It's like trying to find a whisper in a hurricane.
So is the WIMP hunt over? Do we need to completely rethink what dark matter might be?
Not necessarily. This just means we need to broaden our search.
So what are some other candidates for dark matter?
Maybe lighter particles that are more abundant, or perhaps even multiple types of dark matter interacting in complex ways.
So it's less about finding one missing piece and more about discovering a whole dark sector.
Precisely. We might have the entirely wrong puzzle.
Fascinating. But haven't there been recent observations that actually strengthen the case for dark matter? Something about colliding galaxies.
You're talking about MACS J018.5, the new bullet cluster.
Okay, galaxy collisions are pretty common, right? What makes this one so special?
What's unique is how the matter is behaving. We see the hot, glowing gas slowing down as it collides, but most of the mass passes right through.
Like it's not even there.
Exactly, like a ghost. And that's how dark matter should behave. It interacts very weakly with normal matter.
So while the normal matter gets tangled up, dark matter just sails through.
Exactly. Astronomers used a radar gun technique to measure the speeds of the colliding gas and the invisible matter.
It's like watching a cosmic game of billiards, where some balls are invisible.
It's a pretty compelling piece of evidence for something we can't even see.
And just when some physicists were starting to doubt dark matter, boom, this observation comes along.
It throws a wrench in the works. Speaking of mind-blowing observations, let's not forget the James Webb Space Telescope.
Yes, the JWST. It's beaming back incredible images from the early universe.
Like having a time machine, right?
It's revealing a universe that's far more complex than we ever imagined. So what's the JWST been showing us about the early universe?
Well, for one thing, it's discovering surprisingly massive galaxies that seem to have formed much earlier than we thought possible.
So the universe was a lot more active in its early days than we realized.
It seems so. We're also seeing incredibly large black holes that shouldn't exist so early in cosmic history.
Black holes that shouldn't exist. Now that's a mystery.
And the shapes of some of these early galaxies are just bizarre. More like abstract art than the neat spirals and ellipticals we're used to.
Come on, really? Abstract art.
Imagine banana-shaped galaxies.
Banana galaxies. The universe was wild back then.
It definitely challenges our theories about how the early universe evolved.
It's like the universe had a much more chaotic youth than we ever imagined. So what else has the JWST been up to?
Well, it's also provided a new measurement of the universe's expansion rate. And guess what? It doesn't quite match up with other measurements.
Wait a minute, so the universe is expanding, but the rate of expansion might also be changing.
Exactly. And that's fueling the debate known as the Hubble tension.
Oh man, the Hubble tension. That's one of the biggest puzzles in cosmology today.
It really is. We'll need more data to confirm these findings.
But it's clear that the JWST is already revolutionizing our understanding of the universe.
Absolutely. It's a game changer.
Okay, from the vastness of the cosmos, let's zoom in to the microscopic realm now. What's been happening in the world of lab physics?
Well, physicists have been busy manipulating atoms and molecules, creating some truly mind-boggling states of matter.
Really? Like what?
This year, a team in Austria managed to create a super solid.
A supersolid. What's that?
It's a state of matter that's both a solid and a superfluid at the same time.
Wait, a solid that flows? How is that even possible?
Think of a crystal that can maintain its shape like a solid, but also flow without any friction like a liquid.
That's incredible. How do they do that?
They used ultra-cold dysprosium atoms trapped in a laser grid. And they even managed to image these tiny quantum tornadoes that form within the supersolid.
Well, they actually saw quantum tornadoes.
Yep, swirling around inside this bizarre state of matter.
That sounds straight out of a science fiction movie. But why should we care about supersolids? What's the connection to the wider universe?
Well, astrophysicists believe that supersolids might exist inside incredibly dense, rapidly rotating stars called pulsars.
So we're talking about stars that are so dense, a teaspoonful of their matter would weigh billions of tons.
Exactly. And those pulsars sometimes have glitches in their rotation rates, like a cosmic hiccup.
A cosmic hiccup. I like that.
Some scientists believe that these glitches might be caused by the strange behavior of supersolid matter inside these stars.
So from the smallest particles to the largest stars, physics is full of surprises. It's amazing how interconnected it all is.
Absolutely. And that's the beauty of science. It's a constant process of discovery.
Okay, before we get too carried away with the mysteries of the universe, let's ground ourselves in some cutting-edge technology for a bit. Quantum computers are all the rage these days.
They are. And it seems like a particular type is surging ahead. Oh. Tell me more. What kind of quantum computers?
Neutral atom quantum computers.
Neutral atom quantum computers. What makes them so special?
Well, they have a few key advantages. For one thing, they're relatively easy to control and manipulate.
And since they're not charged, they're less susceptible to noise from their environment.
Exactly. That stability is crucial for building reliable quantum computers. In fact, a major breakthrough in 2024 was achieving a fault-tolerant logical computation using a neutral atom system.
Fault-tolerant. What does that mean exactly?
It means that the computation was able to withstand errors. Tiny errors can quickly derail a quantum calculation.
So fault-tolerant means we can correct those errors and keep the computation on track.
Right. It's a huge step towards building reliable quantum computers that could solve real-world problems.
It's amazing to think that we might be on the verge of a quantum computing revolution.
The possibilities are incredible.
But before we get ahead of ourselves, let's take a step back and appreciate another incredible achievement in physics this year. I hear the nuclear clock finally ticked. You heard right. This was a long-awaited milestone. For decades, physicists have been chasing a specific energy transition in thorium atoms.
And why is this energy transition so important?
Because it can be used as a super precise nuclear clock. Imagine a clock so accurate that it would only lose or gain 1 second over the entire age of the universe.
Whoa, that's some serious precision. But why do we need such an accurate clock?
Because by monitoring a nuclear clock, we could detect tiny variations in the fundamental forces of nature.
Wow, really? Like what?
We might discover that gravity isn't as constant as we thought, or that the speed of light has varied slightly over billions of years.
That's mind-blowing. So did anyone actually manage to build this nuclear clock?
Yes. In 2024, not one, but 3 different teams finally nailed the measurement of this crucial energy transition in thorium.
A physics trifecta. Amazing.
It's a huge achievement.
It's like listening for the faintest whisper from the universe. A whisper that could reveal secrets about the very nature of reality.
It really is. And we're just getting started. There's so much more to explore.
This is incredible.
All right, so ready to go even deeper down the physics rabbit hole?
Always. What's next?
Well, this time we're going to get theoretical.
Yeah, bring that.
So you know how physicists have always used equations set in the framework of space and time to describe how particles interact?
Yeah, I mean, that's like physics 101.
Exactly, but now they're exploring a completely new language.
New language.
Yeah, a geometric language.
Geometric, so like shapes and angles.
Yeah, basically they're using curves on surfaces to represent particle interactions.
Okay, so instead of equations in space and time, we're talking geometric shapes and relationships to describe subatomic particles.
You got it.
That's pretty wild.
And you know what's even wilder? It's actually working. This new approach is giving us all sorts of new insights into particles and forces.
Things we thought we understood.
Yep. It's like discovering a hidden code in the fabric of reality.
Okay, I am starting to see why theoretical physics is so mind-bending. And speaking of mind-bending, all this talk about hidden codes reminds me of that negative time experiment that caused such a stir.
Ah, yes, the one that had everyone talking about time travel.
So what was that experiment really about?
Yeah, it definitely got blown out of proportion a bit.
Can you break it down for me? Like, what is negative time anyway?
So, picture this. Physicists shot photons at a cloud of rubidium atoms,
Okay.
and each photon could do a few things. It could excite an atom pass through, or even thanks to quantum mechanics, do both at the same time.
Okay, I remember learning about that. It's like the photons are in multiple states at once, right?
Exactly. And all those possibilities, they interfere with each other.
Like waves in a pond.
Precisely. So now for the negative time part.
Okay, I'm ready?
They were able to measure how long it took for the photons to interact with the atoms, right?
Makes sense.
And for some photons that were absorbed and then re-emitted, it was like they spent a negative amount of time interacting.
Wait, they finished the interaction before they even started.
It's completely counterintuitive. I know, but that's quantum mechanics for you.
So does this mean we can travel back in time?
Not quite. It's more about the weirdness of quantum measurement. It doesn't mean we can actually reverse time in the macroscopic world.
Okay, so no time machine just yet.
Afraid not, but hey, it still shows us how bizarre the quantum world can be.
Right. It really makes me wonder what time even is at that level.
It really does. Speaking of surprises, I was pretty intrigued by this year's Nobel Prize in Physics.
Oh, yeah. Giving it to the AI pioneers. That was unexpected.
It really was, but I think it highlights something important. The lines between different fields of science are blurring.
I see what you mean. So how did AI end up winning a physics Nobel?
Well, back in the 80s, the guys who won, Geoffrey Hinton and John Hopfield, they developed these early artificial neural networks.
The foundation for modern AI. Right?
Exactly, and their inspiration came from statistical physics.
Wow. So they used physics principles to build AI.
They did. They were looking at how systems of many interacting particles behave.
Like what?
Think of the spins in a magnet or atoms in a gas.
And they applied that to computers.
Exactly. Those insights were crucial in developing algorithms that could allow computers to learn from data.
And now we have self-driving cars and all sorts of AI-powered things.
It all goes back to physics in a way.
I guess you could say physics is the foundation for pretty much everything.
In a way, it is.
All right, so blurring boundaries between physics and AI, does that make you wonder about the nature of intelligence itself? Like, can studying AI help us understand the human brain? Or even consciousness?
Whoa, that's a big question, but it's definitely something people are thinking about. We're starting to explore the connections between physics, computer science, and neuroscience.
I wonder if one day we'll be able to use physics to understand the human mind.
That would be incredible, wouldn't it?
It really would.
Yeah.
Okay, need a moment to process all that, but I think we're ready for part 3 of our deep dive.
Sounds good. Let's wrap things up.
All right, so we've talked about dark energy, dark matter, mind-bending experiments, and even the Nobel Prize. But I gotta know, if dark energy really is changing, what happens to the universe?
Well, that's the big mystery, isn't it? The ultimate fate of the universe. If dark energy is constant, like we used to think, then it's probably a big freeze.
Big freeze. Sounds chilly.
Basically, the universe keeps expanding forever, it gets colder and colder, stars eventually die out, and everything just fades to black.
Depressing.
Oh.
But you said if dark energy is constant, what if it's weakening like those hints from DSI? Does the story change?
It could, yeah. Some theories say if dark energy gets weak enough, it might reverse everything. Instead of expanding forever, the universe starts contracting.
Shading too.
A big crunch. Everything collapses back in on itself, the opposite of the Big Bang.
Wow, talk about a plot twist. But wait, there were other possibilities, right? Even weirder ones.
There's the big rip. In that scenario, dark energy doesn't weaken, it actually gets stronger. The expansion accelerates so fast that it rips apart galaxies, stars, even atoms.
Okay, that's definitely not how I want the story to end. So which one is it going to be? Big freeze, big crunch, big rip, or something else entirely?
Honestly, we just don't know yet. It all depends on dark energy, and we need more data to figure it out.
So more observations, more experiments, more mind-blowing discoveries.
Exactly, and that's what makes cosmology so exciting. We're always pushing the boundaries of knowledge, trying to unravel the biggest mysteries of the universe.
Well, I don't know about you, but my brain is officially full. We've covered a lot of ground today. Dark energy, dark matter, quantum weirdness, AI winning a physics Nobel, even those banana-shaped galaxies. It's clear that physics is full of surprises, and there's always more to learn.
Absolutely, and that's the beauty of it. Physics isn't just about equations and theories, it's about exploring the universe and our place in it.
Big thanks to Quanta Magazine for the incredible articles that inspired this deep dive. And to all you listeners out there, thanks for joining us on this cosmic adventure. Keep those minds curious, keep exploring, and we'll see you next time for another deep dive into the fascinating world of physics.